Okay, let's unpack this. In the dizzying, fast-paced world of AI infrastructure, I mean, new tech seems to pop up almost daily, right?
Absolutely. It's hard to keep up sometimes.
Exactly. And certifications, they aren't just, a piece of paper anymore. They're kind of your compass. They guide you through all the complex stuff, validate your expertise, basically tell everyone, hey, I know this stuff.
Right. It's proof you've put in the work.
But we all know the challenge, the real hurdle. How do you actually prepare efficiently? How do you master all these incredibly diverse topics? And crucially, how do you make sure you're ready to pass that exam on the first try?
Yeah, that first try pass is what everyone wants. It's a big investment of time and often money.
It's a mission, really, not just studying.
Absolutely. And today we're embarking on a deep dive, specifically into the NVIDIA Certified Associate AI Infrastructure and Operations, or, NCA-AIIO for sure.
NCA-AIIO, got it.
Yeah. And this isn't just like any exam. It's an entry-level certification, but it's meticulously crafted.
Yeah.
You're really designed for IT pros, data center staff, DevOps folks, system admins, basically anyone who's finding themselves dealing more and more with AI deployment.
Which is a lot of people these days.
A lot of people, it's designed to validate that foundational knowledge across the whole spectrum of AI infrastructure. Everything from, NVIDIA GPU and DPU architectures all the way to the operational best practices you need for managing these demanding AI workloads.
Okay, so it covers the hardware and the operation side.
Exactly. The exam itself, it's 50 multiple choice questions. You get 90 minutes, which is pretty standard. Passing score is 70%.
Okay, 70%.
And what's really compelling, I think, is its accessibility. It's valid for 2-3 years, and there are no prerequisites.
Oh, really? No prereqs?
Nope. Which means pretty much anyone involved in deploying, managing, or even just supporting AI and accelerated computing environments can go for it.
That's great. So our mission today, then, is basically to give you, the listener, a shortcut to being really well-informed, not just about the NCA-AIIO exam specifics, but about the critical underlying concepts that make modern AI actually possible.
Right, the why behind it all.
Exactly. We're going to tackle a pretty comprehensive quiz. We've got 20 challenging questions lined up, spanning all the core domains of the exam.
20 questions. That should cover a lot of ground.
It will, but, and this is important, this isn't just about finding the right answer like some boring test prep. We're going deeper. We're digging into why these are the correct answers, what makes them so important for real-world AI operations.
Yeah, connecting the theory to the practice.
And hopefully uncovering some surprising insights along the way. Think of it as like an interactive deep dive, a collaborative learning thing. We'll unpack common misconceptions, explore practical implications.
Sounds good. Should be fun, too.
Hopefully. So settle in, test your knowledge with us, and get ready for, hopefully some serious aha moments. Moments that leave you not just feeling prepped for an exam, but genuinely more knowledgeable about the whole AI infrastructure landscape.
Let's do it.
All right, let's kick things off with the absolute backbone of AI, the hardware and system architecture. This stuff is truly foundational. It can make or break your AI deployments.
Couldn't agree more. Get the hardware wrong and everything else suffers.
For sure. In fact, this domain alone accounts for a pretty big chunk, roughly 40% of your entire NCA-AIIO score.
Wow, 40%. Okay, so definitely need to know this stuff cold.
Absolutely. Mastering this means you can genuinely design, deploy, and optimize your AI infrastructure right from the ground up. So we're starting right at the core, focusing on GPU architecture fundamentals.
GPU architecture fundamentals.
Okay, first question. Which NVIDIA GPU architecture feature allows partitioning a single physical GPU into multiple isolated instances? The goal here is better resource utilization, especially in multi-tenant environments. Is it A, CUDA cores, the general parallel processing units, B, multi-instance GPU, or MIG, that hardware partitioning tech, C, tensor cores, those specialized AI matrix crunchers, or D, NVLink, the high-speed GPU to GPU interconnect? Take a sec. Think about multi-tenancy isolation. Multi-tenant isolated instances.
Okay.
The correct answer here, pretty unequivocally, is B, multi-instance GPU, MIG.
MIG.
And what's really insightful here, I think, is how MIG fundamentally reshapes resource allocation, especially in shared multi-tenant setups. Before MIG, you often ran into what people call the noisy neighbor problem.
Ah, yeah. Heard of that.
Right. You've got multiple users or apps sharing one powerful GPU. One really demanding workload could just hog all the resources, starve the others, leads to unpredictable performance, lots of frustration.
And probably underutilization, right? Because people just dedicate whole GPUs to be safe. Exactly. Teams would dedicate entire expensive GPUs just to guarantee stability. MIG totally changes that paradigm. It lets you partition a single NVIDIA A100 or H100 GPU into up to 7 independent GPU instances.
7 from one GPU.
Up to 7, yeah. And each of those instances gets its own dedicated memory, its own cache, its own compute cores. It effectively creates these truly isolated, dedicated slices of that powerful GPU.
Like virtual walls inside the GPU.
Pretty much. And this is absolutely vital for environments like cloud service providers, big enterprises, or even, say, internal research labs. Places where multiple AI workloads need to run on shared hardware, but they still need consistent performance and strong isolation.
So it's not just about cramming more jobs onto a GPU. It's making sure they run securely, predictably, without stepping on each other's toes.
Precisely. Predictability and security are key. It's like having several separate high-performance mini GPUs on one physical board.
Okay, that makes sense. But what's the nuance here? You hear about vGPU too, virtual GPU.
Mm.
That also lets you virtualize GPUs, right? How is MIG different? Where does it really shine?
That's a really crucial distinction. So vGPU technology, yes, it also allows for virtualizing GPUs, typically for virtual machines. Think virtual desktops, maybe some lighter AI stuff within VMs.
Okay.
But MIG operates at a much deeper level. It's hardware-level partitioning. vGPU is more like hypervisor-managed resource sharing.
Hardware level versus software level sharing.
Essentially, yeah. MIG offers physical partitioning. Each MIG instance gets its own dedicated hardware resources, memory controllers, L2 cache, streaming multiprocessors, the whole 9 yards.
I see.
This hardware isolation means you get guaranteed quality of service, much stronger security boundaries between tenants. So for cloud providers, that means they can offer more consistent SLAs, service level agreements.
Right, which customers love.
Exactly. And for enterprises, it means more confidence running sensitive, diverse AI workloads on the same server without worrying about data leakage or performance hits from other tenants.
So it gives you the predictability of dedicated hardware, but with the flexibility of virtualization.
You nailed it. It fundamentally changes the economics for cloud providers and the operational efficiency for big companies managing lots of different AI projects where compliance or predictable performance is critical.
That deeper hardware isolation really is a game changer then. Transforms how you manage GPU resources, makes them way more versatile.
Definitely.
Data center infrastructure.
Okay, so we've optimized the individual GPU with MIG. Now, what happens when we scale out? Think entire racks, maybe a whole data center full of these things. How do all these powerful GPUs, nodes, storage systems talk to each other efficiently?
Yeah, the interconnect becomes critical at scale.
Exactly, which brings us to data center infrastructure. So question 2. In a high-performance AI data center, what's the primary advantage of using Infiniband over traditional Ethernet for that internode communication? Your options are A, lower cost per port, B, higher bandwidth and lower latency, C, better compatibility with existing networks, or D, easier configuration and management.
High-performance AI, distributed training.
Yeah.
The answer here is pretty clear-cut. It's B, higher bandwidth and lower latency.
Okay. Speed and responsiveness.
Absolutely. Infiniband really shines here. It delivers incredible bandwidth. We're talking up to 400 gigabits per second now, even higher coming soon. And crucially, ultra-low latency, measured in microseconds, not milliseconds like typical Ethernet.
Microseconds versus milliseconds, that's a huge difference when you're talking scale.
Massive. And if you connect this to the bigger picture, this makes Infiniband the preferred interconnect for distributed AI training and also high-performance computing, HPC clusters. Why? Because it virtually eliminates those communication bottlenecks during large-scale model training.
Okay, explain that bottleneck idea a bit more.
Sure. Imagine you're training a huge language model or a complex computer vision model, and you're doing it across hundreds, maybe even thousands of GPUs.
Right. Big models need big clusters.
Exactly. Those GPUs constantly need to exchange enormous amounts of data, things like model weights, gradients, to synchronize their learning process. If there's any delay in that exchange, if the network is slow, the whole training process grinds down.
So Infiniband basically eliminates those data traffic jams between the GPUs.
That's a great way to put it. It's not just a marginal improvement. It's really an architectural choice that fundamentally enables faster, more efficient, large-scale AI.
But beyond just the raw speed, what are the practical implications? Like for a data scientist waiting for their model or the ops team managing these expensive systems, what does that lower latency really mean?
The practical implications are profound. For data scientists, it means much faster iteration cycles. If a training run that used to take, say, a week on Ethernet now takes maybe 2 days on Infiniband.
Huge difference.
Huge. They can try more models, tweak more hyperparameters, explore more ideas, and ultimately get to better solutions much faster.
And for the ops side,
For operations, it means higher throughput and much better utilization of that extremely expensive GPU hardware. When your GPUs are just sitting there, waiting for data, waiting to sync up.
they're idle. They're burning power but not doing useful work.
Wasted money, wasted time. Exactly. Infiniband ensures those powerful components are working at their peak almost continuously. Think about training a massive model like GPT-3 or something similar across hundreds of GPUs. The speed at which those GPUs can share data is absolutely paramount for efficiency. Infiniband drastically cuts down that idle time.
Directly impacting training speed.
Directly. Which means faster model development, faster deployment. It's why, many of the top AI supercomputers and hyperscale data centers rely on Infiniband for that critical GPU to GPU and node to node communication. It's a cornerstone of cutting-edge AI infrastructure.
So while Ethernet is great for general networking,
Yeah, it's ubiquitous, cost-effective for everyday stuff.
when every nanosecond counts for AI and HPC, Infiniband is really in a league of its own.
Precisely.
Storage architecture.
Okay, let's shift gears a bit and talk storage. Absolutely critical, right? These AI models are just constantly hungry for data.
Insatiable sometimes.
Yeah. And if your storage can't keep up, even the fastest GPUs in the world will just sit there twiddling their thumbs.
Yeah.
Bottleneck.
Yep, storage I/O is a very common bottleneck.
So question 3, which storage configuration best balances performance and capacity for those large AI training datasets? Is it A, a single large SSD, B, a RAID 0 array of NVMe SSDs, C, network-attached storage or NAS, or D, good old traditional hard disk drives?
Okay, balancing performance and capacity for demanding AI training. The optimal choice here is generally B, a RAID 0 array of NVMe SSDs.
RAID 0 of NVMe. Why that specifically?
Let's break down why the others aren't quite the best fit. A single large SSD, while fast compared to hard drives, is still limited by its individual throughput and capacity. You hit a ceiling.
Right, one pipe.
Exactly, traditional hard drives, just too slow. The mechanical latency kills you for AI workloads. And NAS, network-attached storage, can offer capacity or network access, sure, but it often introduces network latency. That can bottleneck high-performance GPUs, especially if the training involves lots of large random weeds.
So the network hop hurts.
It can, significantly. Which brings us back to RAID 0 with NVMe drives. NVMe itself is way faster than older SATA SSDs, uses PCIe directly.
All right, much lower latency interface.
And RAID 0, or striping, essentially combines multiple NVMe drives into one logical volume, reading and writing data across all of them in parallel.
So you aggregate the speed of multiple drives.
Precisely. This configuration gives you extremely high sequential read-write speeds, which is absolutely essential for feeding those data-hungry AI training jobs. And it also lets you scale capacity pretty easily just by adding more drives to the array.
Okay, that makes sense. Like having a super fast race car, but you need a fuel delivery system, the storage that can pump fuel just as fast. Not just quantity, but speed of delivery.
That's a fantastic analogy. It's about sustained raw speed, making sure the entire pipeline is flowing smoothly.
But wait, RAID 0, that doesn't have any redundancy, right? If one drive fails, you lose everything in the array. Isn't that a huge risk for valuable AI datasets?
You've hit on the critical trade-off. You are absolutely right. RAID 0, by design, offers zero fault tolerance. If any single drive in that array fails, boom, all the data in that specific array is gone.
Yikes. So how do people manage that risk in practice?
Well, in these high-performance AI environments, the absolute top priority for the active training dataset is often speed. Speed to keep those incredibly expensive GPUs busy 100% of the time.
Okay, speed above all else for the working set.
For the working set, yes. The strategy usually involves using RAID 0 for that active data during training, but with the crucial assumption that the original authoritative dataset is stored safely and redundantly elsewhere.
Okay. So the RAID 0 is like a high-speed scratch pad.
Exactly. A temporary, super fast working area. The master copy might be on a big, resilient, distributed parallel file system, or maybe in cloud object storage with strong durability guarantees. If the RAID 0 scratchpad fails, it's annoying, sure, but you can quickly recreate it and just recopy the necessary data from that primary redundant source.
I see. So you accept the risk on the temporary storage for maximum speed, knowing the real data is safe elsewhere.
Precisely. That's why it's a common sight in AI labs and data centers where that rapid data access is paramount. If you ever find storage I/O is your bottleneck, and it often is upgrading to a RAID 0 NVMe setup, managed carefully within a larger data redundancy strategy, can give you immediate significant performance gains.
Got it. Important caveat there about the overall strategy.
Power and cooling.
All right, let's talk about something often overlooked, maybe until it's way too late. Power and cooling. These silent partners can completely undermine the best AI infrastructure if you don't get them right.
Oh, absolutely. Seen it happen many times. GPUs generate massive amounts of heat and draw a lot of power.
Exactly. So, question 4. What's the recommended power delivery setup for a high-density GPU server rack to ensure stability and minimize those nasty voltage fluctuations? Your options. A single 240V power supply. B, redundant power supplies connected to different phases. C, just a standard UPS backup. Or D, battery-powered systems.
Stability, minimizing fluctuations, high-density rack. This really raises an important question about fundamental system resilience, protecting your investment. The correct answer, the best practice, is B, redundant power supplies with different phases.
Redundant power supplies, different phases. Okay, why not the others?
Well, a single 240V power supply, A, while common maybe in lower density setups, is a glaring single point of failure. If that PSU goes, your whole server is down.
Right. Not good for long training jobs.
Definitely not. A standard UPS backup, C, is essential for handling external power outages, absolutely, but it doesn't address internal power supply redundancy within the server itself, nor does it help balance the load properly. And battery-powered systems, D, just aren't practical for the continuous high-wattage demands of a dense GPU rack.
So it really comes down to redundancy and resilience within the rack's power delivery. Makes sense. For AI, where training runs can take days, weeks even, an unexpected power hiccup can be catastrophic. Lost progress, corrupted checkpoints, wasted compute time.
Which translates directly to wasted money and time, major setbacks.
But why specifically different phases? Why not just have two redundant power supplies plugged into, say, the same power strip or PDU? What's the advantage of different phases?
That's an excellent clarifying question, because the different phases part is key to true redundancy. If you just have two redundant PSUs connected to the same electrical phase, maybe on the same PDU circuit, you're still vulnerable.
How so?
Well, what if that specific phase in the building has an issue? Or the circuit breaker for that PDU trips? Or the PDU itself fails? Your server still goes down, even with two PSUs.
Ah, okay. The single point of failure just moves upstream a bit.
Exactly. By connecting your redundant power supplies to different electrical phases, meaning they draw power from separate independent circuits, often labeled A and B feeds in data centers, you create a much more robust setup.
True infrastructure-level redundancy.
Right. It dramatically reduces the risk of downtime from a single point of failure anywhere in the power chain, from the utility feed down to the server PSU. If one phase or feed drops, the other immediately takes the full load, ensuring continuous operation.
And it helps with load balancing, too, you mentioned.
Yes, it allows for better load balancing across your data center's electrical infrastructure. As best practice, though, you absolutely must pair this power redundancy with robust cooling strategies.
Ah, the other half of the equation.
Definitely. Things like hot-cold aisle containment, maybe rear door heat exchangers, or even direct-to-chip liquid cooling for the really power-dense systems. You need both stable power and stable temperatures to fully protect that sensitive, expensive GPU hardware. High-density GPU racks generate immense heat, and keeping temps in check is non-negotiable for hardware longevity, consistent performance, and protecting those valuable, long-running AI jobs.
Power and cooling. Got to treat them as a system. Makes perfect sense. Hashtag 2. AI infrastructure fundamentals.
Okay, we've built a solid hardware foundation. Now let's talk about the fundamentals of the AI infrastructure itself. Those core concepts, the enabling technologies that make everything actually run smoothly, the bridge, really, between that raw hardware and productive AI development.
Yeah, the software and concepts that bring the hardware to life for AI tasks. NGC containers.
First up in this section, question 5. What is the main advantage of using NVIDIA NGC containers for AI model deployment? A, they are free to use on any cloud platform. B, they provide pre-configured, optimized environments for AI frameworks. C, they offer the fastest raw GPU performance. Or D, they automatically scale with workload demands.
The main advantage. Okay, the primary benefit, and the correct answer here, is B. They provide pre-configured, optimized environments for AI frameworks.
Pre-configured, optimized environments. Tell me more about why that's the main advantage.
Because it's a massive productivity booster. Let's elaborate.
Yeah.
NGC containers are essentially purpose-built Docker containers. They're highly optimized specifically for popular AI frameworks, think TensorFlow, PyTorch, MXNet, and also for HPC applications.
Okay, so they're tailored for this work.
Exactly. And they come with all the necessary dependencies pre-installed, the right CUDA toolkit version, the right cuDNN library, NCCL for multi-GPU stuff, the compatible GPU drivers. Everything is already baked in, tested, and fine-tuned by NVIDIA engineers.
Oh, wow. That sounds like a huge time saver. Anyone who's wrestled with dependency hell,
Oh, yeah.
conflicting library versions, driver mismatches, spending days just getting the environment set up, they know the pain.
It's a nightmare. NGC containers basically provide a standardized, battle-tested AI operating system for your models.
So it abstracts away all that setup complexity. How does this impact the day-to-day for an AI team? What does it free them up to do?
It fundamentally shifts their focus. Instead of burning precious engineering hours debugging environment setups, making sure things work across different developer machines or servers, they can immediately focus on what truly matters, actually developing, training, and deploying the AI models.
Right. Building the intelligence, not the plumbing.
Exactly. A data scientist can just Docker pull an NGC container, mount their data volume, and start training almost instantly. They know the environment is robust, performant, and optimized.
And for the ops teams deploying these.
It simplifies deployment immensely. It ensures consistency across all environments, from a developer's laptop to staging to production. It virtually eliminates that classic, well, it worked on my machine problem.
Ha! Yes, that one.
Now, are they free to use? A. Yes, the containers themselves are. Do they leverage the fastest GPU performance? C. Yes, because they're optimized. Do they automatically scale? D. No, scaling is handled by your orchestrator, like Kubernetes. But their main advantage, the core value proposition, is providing those ready-to-go, reliable, optimized environments.
It's about reducing friction, enabling rapid iteration, allowing engineers to innovate rather than fight with infrastructure.
Couldn't have said it better myself.
Kubernetes GPU management.
Okay, now here's where it gets really interesting, especially for folks working in those modern cloud-native environments using containers. Question 6. A company wants to deploy AI workloads using containers, and they need a solution that simplifies GPU management within Kubernetes. Which NVIDIA solution should they implement? Is it A. NVIDIA TensorArt, B. NVIDIA NGC Catalog, C. NVIDIA GPU Operator, or D. NVIDIA Base Command?
Okay, simplifying GPU management specifically in Kubernetes. The essential solution for that is C, NVIDIA GPU Operator.
GPU Operator. Why is that the key?
Because it's absolutely pivotal if you want to run accelerated workloads efficiently on Kubernetes without pulling your hair out. Think about what's involved manually. You need to install the correct NVIDIA drivers on every single Kubernetes node with a GPU. Then you need the right CUD toolkits. Then you need to configure the container runtime, like Containered, to be GPU-aware using the NVIDIA Container Toolkit. Then you need to deploy and manage the Kubernetes device plugin so Kubernetes actually knows GPUs exist and can schedule pods onto them.
Wow, okay. That sounds incredibly complex, time-consuming, and super error-prone, especially across a large cluster.
It is. The NVIDIA GPU Operator automates the deployment and, crucially, the management of all those necessary components. Drivers, container toolkit integration, device plugins, monitoring components. It handles the whole life cycle.
So it's like the magic glue, the bridge that makes Kubernetes truly GPU-aware and easy to use for AI. It removes that huge operational burden.
Exactly. It means a developer can just submit their container spec asking for a GPU, and the operator ensures the underlying node is ready, correctly configured, and the GPU is exposed properly to their container.
Okay, but what happens dynamically? Like if a new GPU driver version comes out, or if you add more GPU nodes to the cluster or remove some, does the operator handle that, or is it just a one-time install?
That's precisely where the operator pattern in Kubernetes really shines. The NVIDIA GPU Operator isn't just a static installer script. It's a dynamic, intelligent controller that continuously watches your Kubernetes cluster state.
Like a little robot admin for GPUs.
Kind of. If a new node with GPUs joins the cluster, the operator automatically detects it and deploys the entire necessary software stack, drivers, runtimes, plugins, to make those GPUs usable by Kubernetes pods. No manual intervention needed.
Nice.
Similarly, it can manage driver upgrades across the cluster. You can tell the operator, upgrade all nodes to driver version X, and it handles the rollout safely, node by node. It ensures all your GPUs are running compatible, optimized versions.
That saves a tremendous amount of time and reduces errors compared to trying to do that manually across potentially hundreds of nodes.
Absolutely. It lets engineers focus on the AI, not the infrastructure plumbing. And just for context, the other options. TensorArt A is for optimizing inference performance. NGC Catalog B is where you find those pre-built containers we just talked about. Base Command D is more of a high-level platform for managing AI development workflows and experiments.
Huh.
The GPU operator is distinct. It manages that critical hardware interaction layer specifically within Kubernetes, making sure all those other powerful tools can actually function smoothly and effectively in an orchestrated environment. It's core for agile AI in modern setups.
Makes sense. Very cool tech. Hashtag tag3 AI software stack and frameworks. All right, we've covered the hardware, the foundational infrastructure layer. Now let's climb up the stack to the software itself. This domain is all about how the applications, the AI frameworks actually leverage that powerful hardware we've been discussing. How do you turn raw compute into intelligent results efficiently?
Yeah, how the code actually talks to the silicon.
CU programming model.
Nars up, question 7, digging into CUDA itself. In CUDA programming, what is the primary advantage of using shared memory within a thread block compared to using global memory? Your options. A, is it larger storage capacity? B, higher bandwidth and lower latency? C, automatic memory management? Or D, cross-GPU accessibility?
Okay, shared memory versus global memory in CUDA. This is a really fundamental concept for anyone writing high-performance GPU code. The primary advantage, the correct answer, is B, higher bandwidth and lower latency.
Higher bandwidth, lower latency. Why is that?
Because shared memory provides a significantly faster access path. It's located physically right there on the GPU chip, much closer to the actual CUDA cores doing the calculations. Think of it as the GPU's ultra-fast scratchpad memory.
Like RAM versus your CPU cache.
Exactly. Analogous. It's small but incredibly fast, and all the threads within a single thread block can access it cooperatively. Global memory, on the other hand, that's the main GPU memory, the bigger pool of VRAM. It resides off-chip.
Further away.
Much further away in electrical terms. So while global memory is much larger in capacity, it has significantly higher latency, takes longer to access, and lower bandwidth compared to that on-chip shared memory.
That makes perfect sense. It's like the difference between grabbing something right off your desk versus having to walk down the hall to the filing cabinet. Both hold information, but the access speed is dramatically different.
Great analogy. The desk versus filing cabinet really nails it.
And for AI, where you're often doing these highly parallel, repetitive calculations over and over, those tiny microseconds you save by using shared memory must really add up, right? Leading to big performance wins.
Absolutely. Over the course of billions or trillions of operations in a training run, those small savings accumulate into huge overall speedups.
So what are some real-world scenarios or like common programming patterns where using shared memory makes the most dramatic difference? Where do you see those massive speedups?
That's a great question. Shared memory becomes crucial for any algorithm that exhibits data locality within a thread block, meaning threads within the same block need to access the same or nearby data frequently. A classic example is matrix multiplication.
Okay. Core of many AI ops.
Right. When you're multiplying large matrices, you might assign each thread block to compute a small submatrix, a tile. Instead of every thread in that block repeatedly fetching the same input matrix rows and columns from slow global memory over and over.
Which would be very inefficient.
Very. The threads can cooperatively load the needed tile of data into fast shared memory just once. Then all threads in that block can access that data from shared memory at very high speeds for their calculations. This drastically cuts down on global memory traffic and exposes more parallelism.
So you load once, compute many times from the fast cache.
Exactly. Another common pattern is something like image processing or convolutions. Threads in a block might operate on neighboring pixels. Loading a tile of the image into shared memory allows rapid access to adjacent pixel data without constantly going back to global memory. I've personally seen teams struggle with seemingly fast GPUs that were actually bottlenecked by inefficient memory access. They weren't using shared memory effectively. And then after a simple refactor to intelligently use shared memory where it made sense, they saw massive gains, sometimes 10x, even 100x speedups in specific kernels.
Wow. Just from changing how memory is accessed.
Just from understanding and leveraging the memory hierarchy, this knowledge is absolutely crucial for optimizing performance in GPU computing. It really can be the difference between a slow proof of concept and a truly high-performance, production-ready application.
Fundamental stuff.
Container orchestration, Kubernetes GPU allocation.
Okay, continuing with Kubernetes and the software stack, we talked about the GPU operator making Kubernetes GPU aware. Now let's talk about actually requesting a GPU for your workload. When deploying an AI workload using Kubernetes, which specific resource specification is essential for telling Kubernetes, hey, this pod needs a GPU? Is it a CPU? 4B. NVIDIA.com/check GPU 1C memory, 8G or D storage, 100G.
Right, how do you actually ask for the resource? The correct and absolutely essential specification for GPU allocation within Kubernetes is B, NVIDIA.com/GPU.
1. NVIDIA.com/GPU 1.
Seems specific.
It is. Without that explicit declaration in your pod's resource requests, Kubernetes simply has no idea that your AI workload needs a GPU. It'll treat it like any other CPU-bound workload.
And just schedule it anywhere.
Yeah, it might schedule it on a node without a GPU, and then your application crashes when it tries to access hardware that isn't there. Or if all nodes have GPUs but you didn't ask for one, it might schedule it, but the pod won't actually get allocated the GPU device, again leading to failure.
So it's the explicit signal to Kubernetes, hey, this workload needs dedicated GPU horsepower. Without it, you might as well be asking for a unicorn. It just won't work.
Pretty much. It's a small but absolutely critical piece of YAML or JSON code to unlock that accelerated computing power within your orchestrated environment. Okay, but is it always just a simple one? What if my workload needs, I don't know, half a GPU? Or maybe it needs a specific type of GPU, like an A100 versus an older T4. Can you handle those more granular or specific requests using this mechanism?
That's a great follow-up. It highlights the evolving capabilities here.
Yeah.
So NVIDIA.com/GPU. One is the basic request for one full GPU. But for more granular or specific needs, Kubernetes, working together with the NVIDIA GPU operator we discussed, does offer more sophisticated options.
Like what?
Well, for fractional GPU allocation, if the underlying GPU supports technology like MIG, you could potentially request fractions. The exact syntax might vary, but the concept is there. For example, maybe NVIDIA.com/GPU 0.5 could request half a MIG instance if the admin has configured MIG partitioning that way.
Okay, so fractional use is possible with the right tech.
Possible, yes. More commonly, though, for requesting specific GPU types, you leverage Kubernetes node labeling capabilities.
Ah, labels and selectors.
It's exactly. The GPU operator often helps by automatically labeling nodes based on the GPU models they contain. So a node with an A100 might get a label like gpu.nvidia.com/model.
A100.
Then, in your pod specification, alongside nvidia.com/GPU1, you add a node selector, or a more complex node affinity rule. You can say, I need one GPU, and the node must have the label gpu.nvidia.com/model, A100.
I see. So you ensure your demanding training job lands on the powerful A100.
Right. While maybe a less demanding inference job could be targeted to nodes labeled with gpu.nvidia.com/model in T4, which are often more power efficient for inference.
It ensures your AI workloads get not just any GPU, but the right GPU power they need. Matches hardware capabilities to workload demands. Crucial for both performance and cost efficiency in a mixed GPU environment. It's all part of the contract you establish with Kubernetes for your application's resource needs.
Making container orchestration truly intelligent about acceleration?
ML framework optimization. All right, optimization. Key for efficiency, right. Especially when you're taking AI models out of the lab and into the real world, into production. Question 9. Which NVIDIA software library is specifically designed to accelerate deep learning inference by optimizing those trained neural networks for deployment? Your choices are A, cuDNN, B, TensorRT, NCCL, or D, Kubernetes.
Okay, specifically accelerating inference by optimizing trained models. The library you're looking for there is B, TensorRT.
TensorRT, okay.
Yeah, think about it. You spent maybe days, weeks training this complex deep learning model using a framework like TensorFlow or PyTorch. That raw trained model, while accurate, might not be optimized for peak performance in a production inference scenario where latency and throughput are critical.
Right. Training optimization is different from inference optimization.
Exactly. That's where TensorRT comes in. It takes your trained model as input and essentially recompiles and optimizes it specifically for inference on NVIDIA GPUs.
So TensorRT is like the performance engineer for your already brilliant AI model. It takes the general design and fine-tunes it for the specific NVIDIA hardware it's going to run on in production.
That's a perfect analogy. Performance engineer for your model. It makes it run faster, leaner, more efficiently in that live production setting. It's crucial for making the leap from a research experiment to a scalable real-world service.
Okay, but what exactly does TensorRT do under the hood? What are some of the key techniques it uses that make such a big difference?
It does quite a few sophisticated things. First, a big one is precision calibration. It can often take a model trained in FT32, 32-bit floating point, and convert parts, or all of it, to use lower precision, like FP16, half precision, or even INT8, 8-bit integers.
Without losing too much accuracy.
Exactly. It includes calibration steps to minimize accuracy loss, and lower precision means less memory needed, faster data transfers, and faster computation on hardware that supports it, like tensor cores.
Okay, lower precision. What else?
Second, it performs layer fusion. It intelligently combines multiple layers or operations in the neural network graph, things like a convolution, followed by a bias add, followed by a real U activation into a single optimized kernel.
Ah, reducing overhead.
Precisely. Fewer kernel launches, less data movement between operations. Third, it does kernel auto-tuning. It actually selects the best specific algorithms and CUDA kernels for the layers in your model on the specific target GPU utility you're deploying on. NVIDIA has this vast library of optimized kernels, and TensorArt picks the fastest ones for your exact situation.
Wow, that's very targeted.
It is. Plus, it does things like eliminating layers that don't contribute to the output, optimizing memory reuse, the whole 9 yards for inference speed.
So all these optimizations together.
They directly relate to performance. They allow you to get way more out of your deployed AI models. It can drastically reduce model size, increase inference throughput, sometimes by orders of magnitude, and significantly lower latency. This often makes the crucial difference between a model being just a cool demo and being a truly production-ready application that can handle real-time demands at scale. Think autonomous driving, real-time translation, medical imaging.
Anywhere speed and efficiency at inference time really matter.
Exactly. TensorRT is pretty much an indispensable tool for anyone deploying AI seriously, whether at the edge or in big data centers.
Got it. TensorR2 for inference optimization. Hashtag tag RIV found data management and storage. All right, let's talk data. As we all know, data is the absolute lifeblood of AI. Without good data and lots of it, your models are just fancy algorithms.
Garbage in, garbage out, as they say.
Exactly. And with data sets growing exponentially, how we manage and store those massive repositories efficiently becomes a huge potential bottleneck if we don't handle it right.
Yep, storage can definitely gate your performance.
So let's dive into the strategies for effective data management and storage for AI.
Distributed storage systems.
Question 10. When you're designing a distributed storage system specifically for these large-scale AI training datasets, which storage pattern usually provides the best balance of performance, scalability, and fault tolerance? Your options are A, a single centralized NAS, B, a distributed parallel file system with beta striping, C, just local storage on each compute node, or D, cloud storage accessed over the internet.
Okay, large-scale AI training, petabytes of data, maybe thousands of GPUs needing access, thinking about performance, scalability, and fault tolerance. The optimal choice here is generally B, a distributed parallel file system with beta striping.
Distributed parallel file system. Why is that better than the others for this use case?
Let's look at why the others fall short for large-scale training. A single centralized NAS, while often easier to manage initially, quickly becomes a massive performance bottleneck. All that I/O traffic from potentially hundreds of GPUs has to go through one central point. It just can't keep up.
Right, the single choke point kills you.
Exactly. Local storage only on each node C is fine for smaller independent tasks, maybe inference, but completely impractical for truly large shared data sets needed for distributed training, where all nodes need access to the same massive pool of data.
Yeah, can't copy petabytes to every node.
No way. And cloud storage accessed over the internet, while offering immense scalability and durability, often introduces significant network latency. Sending data requests back and forth to S3 or Google Cloud Storage can really hinder high-performance, tightly synchronized training jobs where GPUs need data now.
It's excellent for archiving, data lakes, maybe slower batch jobs, but less ideal for the absolute fastest access needed during core training phases.
Okay, so that leaves the distributed parallel file system. What makes it the best fit?
These systems, think things like Lustre or IBM Spectrum Scale, formerly GPFS or BGFS, are specifically designed for this kind of high-performance, large-scale workload. They work by distributing data across many storage servers and allowing parallel access.
So multiple storage servers work together to serve data. Exactly. Data is often striped across many disks and many servers. When your compute nodes request data, they can read different pieces from multiple storage servers simultaneously. This provides incredibly high aggregate bandwidth, meaning the total speed scales up as you add more storage servers. It effectively eliminates that single choke point of a NAS.
Ah, parallel access matching the parallel compute of the GPUs.
Precisely. They also typically have built-in redundancy and data protection schemes like erasure coding or replication, so you don't lose data if a drive or even a whole storage node fails. And they're designed to scale out to petabyte capacities and beyond.
So it's not just throwing a lot of hard drives at the problem, it's architecting them to work together intelligently, ensuring that data flows as fast as the compute needs it.
You got it. This distributed parallel approach is really the only way to keep those powerful GPU clusters fully fed and working at maximum efficiency when you're dealing with truly massive data sets in high-performance training.
But it sounds powerful, maybe also complex. What are the operational challenges compared to just setting up a NAS?
You're absolutely right. While immensely powerful, these systems definitely introduce a different level of operational complexity compared to a simple NAS box. The initial setup and configuration can be complex, often requiring specialized expertise.
Need people who know Lustre or GPFS.
Yeah. Management and monitoring can also be more involved. Tuning the network, the storage servers, the client-side settings for optimal performance requires careful effort. However, for any organization serious about doing large-scale, high-performance AI training efficiently, the investment in understanding and deploying this kind of architecture is pretty much non-negotiable. It connects directly back to our hardware concepts, ensuring your storage doesn't become the bottleneck, preventing your expensive GPU race cars from constantly running out of fuel.
Makes sense. The right tool for the job, even if it's more complex to wield.
Data pipeline optimization.
Okay, so we have the storage system, but just having fast storage isn't enough. The process of actually loading the data from storage, maybe doing some pre-processing, and getting it onto the GPU fast enough, that whole pipeline can still be a major bottleneck.
Absolutely. The data loading pipeline is often the silent killer of GPU utilization.
Right. You've got this amazing data set, amazing storage, amazing GPU, but if you can't bridge the gap efficiently, the GPU sits idle. So question 11. In an AI training pipeline, what's the most effective strategy to minimize these data loading bottlenecks, especially when training with large data sets? Is it A, load the entire data set into GPU memory at the start? B, implement asynchronous data loading with prefetching? C, process data sequentially without any caching? Or D, compress all the data during the training process?
Okay, minimizing data loading bottlenecks with large data sets. The most effective strategy here is definitely B, implement asynchronous data loading with prefetching.
Asynchronous loading with prefetching, let's break that down. Why not the others first?
Sure. Option A, load the entire data set into GPU memory. Generally impossible for large data sets. Modern data sets are often terabytes, GPU memory is gigabytes. Just won't fit.
Right. Obvious limitation.
Option C, process data sequentially without caching. That would be incredibly inefficient. Your GPU would finish a batch and then just wait, while the CPU slowly fetches and processes the next batch sequentially. Terrible utilization.
Okay. And D, compress data during training.
Compressing data might save storage space or network bandwidth if you're reading remotely, but doing the decompression during training would likely add significant CPU overhead and delay, probably making the bottleneck worse, not better.
Okay, so that leaves B, asynchronous loading with prefetching. What does that actually mean? How does it work?
It means overlapping computation with data loading. While the GPU is busy crunching numbers on the current batch of data, batch N, the CPU is already working in the background to load, preprocess, and prepare the next batch, batch N+1.
Working ahead.
Exactly. The CPU gets batch N+1 ready, and maybe even transfers it to a staging area in the GPU's memory before the GPU is even finished with batch N. As soon as the GPU finishes batch N+1 is immediately available for it to start working on.
So the GPU never or rarely has to wait for data.
Ideally, yes. The goal is to keep the data pipeline always one step ahead of the GPU. This significantly maximizes GPU utilization, prevents it from sitting idle, just waiting for data.
That sounds brilliant. Like a perfectly tuned assembly line where no station is ever waiting for parts. The GPU just keeps churning because the next piece is always ready.
That's a great way to visualize it. This proactive asynchronous approach is truly essential for maximizing the return on investment from your expensive GPUs.
But practically, how do you do this? How is it implemented in common frameworks like PyTorch or TensorFlow? Are there specific tricks or APIs?
Thankfully, modern AI frameworks are designed with exactly these optimizations in mind. It's often built in, you just need to enable it correctly. In PyTorch, for instance, the data loader class is key. When you create a data loader, you can specify num workers. Setting num workers to a value greater than 0 tells PyTorch to use separate background processes to load the data in parallel, asynchronously.
Using multiple CPU cores for loading.
Right. And another common setting is pin memory. True. This tells the data loader to put the loaded data into special pinned host memory, which allows for much faster asynchronous data transfers from the CPU RAM to the GPU memory.
So num workers plus pin memory in PyTorch.
Those are the big ones. TensorFlow has similar mechanisms, often through its tf.data API. You can use methods like .map with parallel calls for preprocessing and, crucially, .prefetch. The .prefetch method explicitly tells TensorFlow to prepare one or more batches in advance while the model is training on the current batch.
So the frameworks provide the tools, you just need to use them correctly.
Exactly. These built-in capabilities allow that clever overlap. The data loader prepares the next batch while the GPU processes the current one. It's fundamental to optimizing performance for pretty much any data-intensive AI workload. Keep that pipeline full.
Awesome advice. #V. Deployment and operations. Okay, we've designed the system, figured out how to feed it data efficiently. Now let's move into the real world. Deployment and operations. This is where AI systems go from being prototypes in a lab to live, production services, and keeping them running smoothly, reliably, efficiently. That's a whole different challenge.
Yeah, MLOps is a huge field in itself for good reason.
Yeah.
Getting models into production and keeping them there reliably is hard.
Container orchestration. Kubernetes GPU utilization.
Let's revisit Kubernetes again, but from an operational utilization perspective. Question 12. When you're deploying AI workloads using Kubernetes, which scheduling strategy is best for ensuring optimal GPU resource utilization, especially if you have a heterogeneous cluster, meaning a mix of different GPU types? Is it A, random pod scheduling, B, node affinity using GPU type labels, C, first available node scheduling, or D, CPU-only scheduling?
Okay, optimal utilization across a heterogeneous GPU cluster. This is a common real-world scenario. The best strategy here is clearly B, node affinity with GPU type labels.
Node affinity with labels again.
Right.
Why is that optimal for utilization specifically?
Let's rule out the others. Random pod scheduling, A. Terrible for utilization. Your super demanding training job might land on a low-power inference GPU, run slowly, and waste resources, while a powerful training GPU sits idle.
Right. Mismatched resources.
First available node scheduling, C. Similar problem. It just picks the first node with any available GPU slot without considering if it's the right GPU for the job. Again, leads to mismatches and inefficient use. And CPU-only scheduling, D, is obviously irrelevant for GPU workloads.
Okay, so B avoids those mismatches. How does that lead to optimal utilization?
Because it allows you to intelligently direct workloads to the most appropriate hardware. As we discussed before, you label your nodes based on the GPU model, A100, T4, V100, etc. Then your workload definitions use node affinity rules to say, I need an A100, or I'd prefer a T4, but a V100 is okay.
So you match the job's requirements to the hardware's capabilities.
Exactly. This ensures that your most demanding, compute-intensive training jobs land on your most powerful GPUs, like A100s or H100s, maximizing their usage for the tasks they excel at. Meanwhile, less demanding tasks, like inference serving, which might be more sensitive to cost or power, can be directed to GPUs optimized for that, like T4s.
Preventing the scenario where a simple inference job ties up an expensive A100 that a big training job desperately needs.
Precisely. It prevents resource waste and ensures that each type of GPU is being used for the workloads it's best suited for. This maximizes the overall throughput and efficiency of your entire heterogeneous cluster. It's about smart placement, the right tool for the right job, driven by those labels and affinity rules.
This seems critical for any organization with a mix of GPU hardware trying to maximize their investment.
It really is. It's how you translate that infrastructure knowledge, knowing what each GPU is good at, into efficient, intelligent operations using Kubernetes scheduling capabilities.
Makes perfect sense.
Blue-green deployment.
All right, deployment updates. Always a bit nerve-wracking, right? Especially with AI models where even small changes in the new version could have unexpected, maybe negative consequences in production.
Yeah, deploying a new model version always carries some risk. You need strategies to manage that.
Definitely. So question 13. When you're implementing a blue-green deployment strategy for AI model updates, what is its primary advantage compared to doing, say, a rolling update in a production environment? Your options. A, does it use less computational resources? B, does it enable instant rollback and eliminate version mixing? C, does it require no additional infrastructure? Or D, does it automatically test model accuracy?
Okay, blue-green versus rolling updates for AI models. The primary advantage of blue-green in this context is B, enables instant rollback and eliminates version mixing.
Instant rollback and no version mixing. Let's unpack that. How does blue-green work first?
Sure. The basic idea of blue-green is you maintain two identical production environments. Let's call the current live stable one blue.
Okay, blue is live.
Right. Then you set up a second identical environment, green. You deploy your new AI model version entirely to the green environment. Crucially, green doesn't receive any live user traffic yet.
So it's like a staging environment, but production scale.
Exactly. You can fully test the new model in green run integration tests, maybe even shadow traffic, whatever you need, without affecting any real users. Once you're completely confident that the new model in green is working correctly and performing well,
Then you flip the switch.
precisely, you instantly switch all the incoming user traffic from the blue environment to the green environment. Now, green is live and blue is idle.
Okay. And the instant rollback part.
If after switching, you detect any problems with the new model in green, unexpected errors, poor performance, bad predictions, you can instantly switch the traffic right back to the stable blue environment, which is still running the old known good version.
Minimal downtime, minimal user impact. That's huge for critical AI applications.
It is. Compare that to a rolling update, where you're slowly replacing old instances with new ones. If you find a problem halfway through, rolling back can be complex and messy, and users have already been exposed to the buggy version.
Right. And what about the eliminates version mixing part?
That's also key. In a rolling update, for a period of time, you have both the old and new model versions serving traffic simultaneously. This can make monitoring tricky, debugging harder, which version caused the error, and A/B testing results confusing. Blue-green gives you a clean, immediate cutover. At any given time, all users are hitting either the old version or the new version, never a mix.
Much simpler to manage and reason about?
Definitely. Now, does it use less resources? A. No, it usually requires more resources, at least temporarily, because you need two full environments. Does it require no additional infrastructure? C. Clearly false. Does it automatically test accuracy? No, testing is a separate step you perform on the green environment before switching, but the strategy itself doesn't do the testing.
So the core benefits are that instant safety net of rollback and the clean separation of versions.
Exactly. For mission-critical AI, where model behavior is paramount and downtime is costly, blue-green often offers superior control and safety, despite the extra resource costs.
Makes a lot of sense for high-stakes deployments. Hashtag tag me size. Performance optimization and monitoring. All right, performance. In AI, it's absolutely paramount, isn't it? Every millisecond of latency, every watt of power, every percentage point of GPU utilization, it all adds up.
It really does. Optimization and monitoring are continuous efforts, not one-time tasks.
So true. Let's delve into the essential tools and strategies for both squeezing the maximum performance out of your infrastructure and keeping a close eye on its health and efficiency.
GPU monitoring tools.
Question 14. Which NVIDIA tool provides the most comprehensive real-time monitoring of things like GPU utilization, memory usage, temperature, power consumption, etc., especially across multiple GPUs in a data center environment? Is it A, the command line tool NVIDIA SMI, B, NVIDIA Data Center GPU Manager, or DCGM, C, the CDA Profiler, or D, TensorBoard?
Okay. Comprehensive, real-time monitoring across multiple GPUs in a data center. While NVIDIA SMI is super useful for quick checks on a single machine.
Yeah, everyone uses NVIDIA SMI.
Right. It's the go-to for a quick look. And the CUD profiler, C, tools like Nsight Systems or Nsight Compute, are for deep diving into kernel performance, not really for general monitoring. TensorBoard D is mainly for visualizing ML training metrics like loss curves, not hardware stats. So the most comprehensive tool specifically for data center scale multi-GPU monitoring is B, NVIDIA Data Center GPU Manager, DCGM.
DCGM.
Okay.
So that's the enterprise-grade solution.
Exactly. It's designed specifically for managing and monitoring GPU fleets at scale, like in a large cluster or data center.
So it's a big step up from just running NVIDIA SMI on each machine individually. It sounds like it gives you that central mission control view for your whole GPU fleet.
That's a perfect way to put it. Mission control. It transforms individual device stats into a cohesive, system-wide operational view.
What kind of extra information or capabilities does DCGM give you that NVIDIA SMI might miss? And how does it fit into existing data center monitoring systems people might already have?
Great questions. DCGM provides a much richer set of telemetry and diagnostics compared to NVIDIA SMI. Beyond the basics like utilization, memory, temp, and power, it exposes more detailed metrics. Things like clock speeds over time, PCIe, bandwidth usage, NVLink traffic stats between GPUs, crucial ECC memory error rates.
Oh, ECC errors. That's important for data integrity.
Very important, especially for scientific computing or long training runs. DCGM also monitors specific hardware component temperatures, not just the overall GPU temp, and it can provide health warnings and even predictive fault indicators based on telemetry patterns.
Wow, okay, so it's much more proactive and detailed.
Definitely. But what makes it truly powerful for operations is its integration capabilities. DCGM exposes a comprehensive set of APIs. There are bindings for Python, C, Go. This allows you to easily pull all these rich metrics into your existing data center monitoring and observability platforms.
Like Prometheus and Grafana.
Exactly the common ones. You can feed DCGM metrics straight into Prometheus, build detailed Grafana dashboards showing historical trends, GPU health across the whole cluster, utilization patterns, and you can set up automated alerting based on DCGM metrics.
Yeah.
Get an alert if a GPU overheats, or if ECC errors start climbing, or if utilization drops unexpectedly.
So you can monitor thousands of GPUs from a single pane of glass and get alerted proactively before a small issue becomes a major outage.
Precisely. It offers that in-depth data center level monitoring essential for managing complex AI deployments effectively, gives you that holistic view of your entire GPU fleet's health and performance, ensuring maximum uptime and optimal resource use.
Very cool. DCGM for serious monitoring.
Performance bottleneck identification.
Right. Here's a classic troubleshooting scenario. I bet many listeners have hit this one. An AI training job is running, but you check the monitors, and you see really low GPU utilization, maybe only 30%. Yet the CPU cores on the machine are totally pegged, running at 100%. What is the most likely cause of this performance bottleneck? A, is it insufficient GPU memory? B, a data loading and pre-processing bottleneck? C, network bandwidth limitations? Or D, faulty GPU hardware?
Yes, the busy CPU, lazy GPU problem, very common. Okay, considering those symptoms, high CPU usage, low GPU utilization, the most likely culprit, almost invariably, is B, a data loading and pre-processing bottleneck.
The data pipeline strikes again.
It often does. Let's quickly think why the others are less likely. Insufficient GPU memory, A, that usually results in out-of-memory errors, forcing you to reduce batch size or maybe very low utilization if you manage to run with the tiny batch, but typically not high CPU usage alongside it.
Yeah.
Network bandwidth limitations, C. That's more likely to show up as a bottleneck in distributed training, where GPUs across nodes are waiting for each other. For a single node showing this pattern, it's less likely unless the data itself is being streamed slowly over the network.
Right. And faulty GPU hardware, D.
Faulty hardware would probably lead to outright errors, crashes, maybe weird graphical artifacts, or even zero utilization. Not typically this specific pattern of low but steady GPU use with a maxed out CPU.
Okay, so it really points back to the CPU being the bottleneck, unable to feed the GPU fast enough.
Exactly. The GPU, powerful as it is sitting there ready to work, but it's starved of data because the CPU is working frantically but failing to keep up with loading, decoding, augmenting, transforming, and transferring the data.
That's such a critical insight. It's not always about needing a faster GPU. Sometimes you need to fix the pipeline feeding the GPU. A system's only as fast as its slowest part. So within that data loading and pre-processing category, what are some specific common culprits? What makes the CPU work so hard but still fall behind? And what are the first steps someone should take to diagnose and fix this?
Good question. Common culprits include
slow underlying storage. If the dataset lives on slow spinning disks or a heavily congested network file share, the CPU just spends ages waiting for I/O.
checking IO stat or IOTOP.
Yep. 2, inefficient preprocessing code. Maybe the data augmentation functions are written inefficiently in Python, or complex transformations are happening sequentially on the CPU instead of being parallelized or even offloaded to the GPU if possible.
Right, CPU-bound transformations.
3, lack of asynchronous loading prefetching. We just talked about this. If the pipeline is synchronous load, process, train, repeat, the GPU waits while the CPU loads and processes, you need that overlap.
Using num workers and prefetch.
Exactly. 4, suboptimal data formats. Reading data from millions of tiny individual files can have huge I/O overhead compared to reading from larger optimized file formats like TF-Record, Parquet, or Web Dataset.
Okay, lots of potential issues in the pipeline. How to diagnose?
First step is usually profiling. Use the built-in profilers in PyTorch or TensorFlow. They can show you exactly where the time is being spent. Is it disk I/O? Is it a specific preprocessing function on the CPU? Is it the data transfer to the GPU?
Pinpoint the bottleneck within the pipeline.
Right. Then you address it, maybe upgrade storage, optimize the slow preprocessing functions, maybe use libraries like DLI or Rapids. Make sure you're using multiple data loader workers and prefetching effectively. Consider converting your dataset to a more efficient format. Fixing this often unlocks huge GPU utilization gains, sometimes doubling or tripling your training speed without touching the model code itself.
It really highlights how interconnected everything is: storage, CPU processing, GPU compute. You need to optimize the whole system.
Totally. #TechHedgeLAZA. Security and compliance.
Okay, shifting gears again. In today's world, security and compliance, they aren't just like optional nice-to-haves, are they? They're absolutely non-negotiable foundations for any serious AI infrastructure.
Couldn't agree more, especially with the sensitivity of data often used in AI and the power of the infrastructure itself. Breaches can be catastrophic.
Exactly. So let's explore how to protect those invaluable AI assets: the data, the models, the compute resources.
Role-based access control.
First up, question 16. In a multi-tenant AI infrastructure where you might have different teams or users sharing resources, which access control strategy provides the best balance of security and operational flexibility? A single shared administrator account for everyone. B, role-based access control, RBAC, combined with the principle of least privilege. C, just no access controls at all. Or D, simple password-only authentication.
Okay, this one should hopefully be straightforward for anyone working in IT. The optimal strategy, really the only viable and secure strategy for any shared infrastructure, let alone AI, is B, role-based access control, RBAC, with the least privilege principle.
RBAC with least privilege. Why are the others so bad?
Well, a single shared admin account. A, that's a security nightmare. No accountability, massive blast radius if compromised. Just don't do it.
Right, terrible idea.
No access controls. See,
Yeah.
I mean, that's basically leaving the doors wide open. Unthinkable in any professional setting. And password-only authentication, D, well, obviously a part of security, is totally insufficient on its own. It's authentication, who you are, not authorization, what you're allowed to do. You need both.
Okay, so RBAC provides that authorization piece. Define roles, assign permissions, and the least privilege part means you only give people the absolute minimum access they need to do their job, nothing more.
Exactly. It's a foundational security principle that scales beautifully, from small teams to huge, complex organizations. It's all about defining who can do what and strictly limiting potential exposure. Absolutely critical when you're dealing with powerful, shared AI infrastructure and potentially very sensitive data.
But in the specific context of AI, what would be some examples of typical roles and the kinds of privileges you'd assign or deny? How does RBAC prevent specifically AI-related security mistakes?
That's where it gets practical. In a typical AI environment, you might define roles like data scientist, maybe needs read access to certain approved data sets, permission to submit training jobs to specific resource queues or namespaces, ability to view logs for their jobs. But critically, not permission to modify core infrastructure components, delete production models deployed by others, or access raw sensitive data they haven't been explicitly granted.
Okay. Restricted to their research and training tasks.
Right. Then maybe an MLOps engineer needs permissions to deploy models to inference endpoints, manage Kubernetes resources related to serving, monitor performance, maybe troubleshoot infrastructure issues. But perhaps they don't need access to the raw training data itself.
Focused on deployment and operations.
Exactly. You might have a data engineer. Needs read-write access to data lakes or storage buckets where raw data lands, ability to build and manage data pipelines like ETL jobs, but not permissions to train models or manage GPU clusters directly.
Segregation of duties.
Precisely. And then maybe an administrator with broader access. But even their actions should be heavily audited, and they should ideally use temporary elevated privileges only when necessary, still adhering to least privilege where possible.
How does this prevent AI-specific issues?
It directly prevents common mistakes or malicious actions. For instance, a data scientist accidentally deleting a critical production model because the permissions were too broad. Or an MLOps engineer inadvertently accessing highly sensitive personal data stored in a training bucket that they don't actually need for their deployment tasks. RBAC ensures accountability. You know who did what, drastically reduces the attack surface, compromising one account has limited impact, and limits the potential damage from errors or breaches.
Yeah.
It's essential for protecting the infrastructure, maintaining data privacy and integrity, and meeting compliance regulations like GDPR or IPF.
Foundational security for AI.
Data encryption standards.
Let's talk data encryption, especially for those AI training data sets that might contain sensitive information, personal data, financial data, medical data. Question 17. Which encryption approach provides the most comprehensive data protection throughout its life cycle? Is it A, encryption at rest only, B, encryption in transit only, C, end-to-end encryption, covering data at rest, in transit, A and D in use, or D, no encryption needed because it's all internal data?
Okay, comprehensive protection for sensitive AI data. The answer you need is C, end-to-end encryption, at rest, in transit, and in use. Relying on just one piece, like only encrypting data stored on disk at rest or only encrypting it while it travels over the network in transit, leaves significant gaps.
Why is that? Data isn't static, right?
Exactly. Data is constantly moving and being processed. If you only encrypt it when it's sitting still on a disk at rest, it's vulnerable while traveling across the network to the compute node or while it's sitting in memory being processed by the CPU or GPU. If you only encrypt it in transit, it's vulnerable the moment it lands on disk or gets loaded into memory. Option D, no encryption for internal data, is just negligent in most modern security contexts.
So end-to-end aims to cover all those states. Data on disk, at rest, data on the network, in transit, and data in memory being processed in use.
Correct. That's the goal of a truly comprehensive strategy. Encrypt the storage volumes, use TLS-SSL for all network communication, and protect the data while it's actively being computed on.
Okay, encryption at rest and in transit seem relatively standard these days. Storage systems often offer built-in encryption, and TLS is ubiquitous for networks. But that in-use part, protecting data while it's actively being processed in memory or on the GPU itself, that sounds tricky, especially without killing performance. How is that typically handled?
You've hit on the most challenging part, and honestly, the area that's still evolving the most rapidly. Encryption in use, or more broadly, confidential computing, is indeed the frontier, particularly for high-performance stuff like AI on GPUs.
So how does it work conceptually?
Traditionally, yeah, data had to be decrypted when loaded into CPU or GPU memory for processing. That created that vulnerable window. Confidential computing aims to close that window using hardware-based technologies. Things like Intel's SGX, software guard extensions, or AMD's SEV, secure encrypted virtualization, create secure enclaves.
Secure bubbles within the processor?
Kind of. They provide trusted execution environments, TEs, where data can remain encrypted even while it's sitting in RAM, or where the computation itself happens within an isolated encrypted region, protected even from the host operating system or hypervisor.
Okay, that's for CPUs. What about GPUs?
That's been tougher, but NVIDIA is actively working on this too. They have initiatives around confidential computing for GPUs, leveraging technologies like secure virtualization on the host CPU, combined with features on the GPU itself, especially with things like secure modes for MIG instances, to extend that protection boundary to the GPU's memory and compute units.
So it's an active area of development.
They're very active. These technologies are still maturing, they can sometimes introduce performance overhead, and they require careful implementation. But they represent the future of achieving true end-to-end protection. So that comprehensive strategy, encrypting data at rest, in transit, and leveraging confidential computing techniques for encryption protection in use where feasible, is crucial. It directly connects to robust data management and is absolutely vital for meeting stringent data protection regulations like GDPR, IPA, CCPA, especially when dealing with sensitive personal, financial, or medical data and AI models. It's about creating that complete security perimeter around your information, no matter where it is or what state it's in.
Fascinating. And clearly essential moving forward. Hashtag tag 88. Troubleshooting and maintenance. All right, let's face reality. Even the most carefully designed, most robust AI systems, they're going to hit issues sometimes. Things break, performance degrades, errors pop up.
It's inevitable in complex systems. Knowing how to troubleshoot effectively is a critical skill.
Absolutely. Knowing how to systematically troubleshoot and properly maintain your AI infrastructure is vital for minimizing that costly downtime, preserving valuable compute cycles, and just ensuring continuous, reliable operation.
GPU failure diagnosis.
So first troubleshooting scenario, question 18. You've got a GPU that's showing intermittent errors during AI training jobs. Not failing completely, but throwing errors sometimes, maybe crashing jobs randomly. This can be super frustrating to diagnose. Which diagnostic approach should you perform first to try and identify the root cause? A, just replace the GPU immediately. B, check the thermal sensors and power delivery logs first. C, reinstall the CUDA drivers. Or D, run stress tests only.
Ah, the dreaded intermittent error. Those are the worst.
Okay.
The first, most logical and often most revealing step here is B. Check thermal sensors and power delivery logs.
Check the environment first. Why that before the others?
Because intermittent issues with complex hardware like GPUs are very often caused by environmental factors, heat or power instability. Replacing the GPU immediately, A, is jumping the gun. It's expensive, time-consuming, and might not even fix the problem if the issue is the slot, the power, or the cooling.
Right. Don't swap parts blindly.
Reinstalling CUDA drivers, C, is a valid troubleshooting step for software-related glitches, but usually after you've ruled out more fundamental hardware and environmental causes. And just running stress tests, D, is useful for reproducing the intermittent issue perhaps, but without looking at the logs during the stress test, you don't know why it might be failing. The logs provide the context.
So start with the simplest, most common physical culprits. Heat and power. It's the smart, systematic approach.
Exactly. Don't immediately jump to the most complex or expensive potential solution.
But when you say intermittent errors, what kind of specific symptoms might you see? And what would those thermal or power logs actually tell you? What patterns would be a red flag?
Good question. Intermittent errors could manifest as training jobs just crashing randomly with maybe a generic CUDA error or even a system hang. Or maybe the model's accuracy suddenly plummets inexplicably mid-run. Or specific math operations start returning nans, not a number.
Okay, weird, inconsistent behavior.
Right. When you check the thermal sensors using tools like NVIDIA SMI, or even better, the historical data from DCGM, you're looking for temperature spiking or consistently staying above the GPU's recommended operating limits.
Yeah.
That's often 80–90 degrees Celsius under load. Depends on the specific card model.
And high temps lead to?
Sustained high temps often lead to thermal throttling. The GPU automatically slows itself down, reduces clock speed to prevent overheating and damage. This throttling can cause performance drops, instability, or calculation errors. The logs would show you those high temps correlating with the times the errors occurred.
Okay. And the power logs?
For power delivery logs, again, DCGM is great here, or logs from smart PDUs, you're looking for signs of instability. Are there significant voltage fluctuations? Is the power draw spiking right before an error occurs, maybe exceeding the power supply's rating? Are there sudden drops in wattage being delivered? A GPU starved of stable, sufficient power can absolutely behave erratically, leading to compute errors or crashes.
So checking these environmental conditions first is quick, uses readily available tools, and often points directly to the root cause.
Very often. It lets you fix the cooling or power issue before you waste time reinstalling drivers or RMAing a potentially perfectly good GPU. It builds directly on that hardware knowledge we discussed earlier, the importance of robust power and cooling. Ignoring the environment is a common and costly troubleshooting mistake.
Sound advice. Check the vitals first.
Network connectivity issues.
Okay, let's move to a distributed training scenario. Multiple nodes working together. Now you start seeing sporadic communication failures between the nodes. Maybe jobs stall waiting for synchronization, or you get NCCL errors about timeouts or unreachable peers. What's the most systematic approach to diagnose this kind of intermittent network issue in a distributed setup? Your choices: A, just restart all the training jobs and hope it goes away. B, methodically test connectivity layer by layer. Physical, then network, then application. C, immediately start replacing network switches. Or D, just blindly increase the network timeouts in the application.
Troubleshooting distributed systems networking. Fun times. This definitely raises an important question about being systematic versus just trying random things. The most systematic and effective approach here is B, test connectivity layer by layer. Physical, network, application.
Layer by layer. Why is that better than the others?
Well, restarting jobs, A, that might clear a temporary glitch, but it doesn't find or fix the underlying root cause. The problem will likely just come back.
Right. Treating the symptom, not the disease.
Replacing switches, C, that's the shotgun approach. Super expensive, disruptive, and completely unnecessary if the problem is just a bad cable or a software configuration error you diagnose before replacing hardware.
Definitely. And increasing timeouts. D.
Just increasing timeouts might make the job seem to fail less often because they wait longer, but it doesn't fix the actual communication problem. It just masks it and probably makes your overall training much slower because everything is waiting longer during those communication steps. Plus, it can hide real issues until they become catastrophic.
Okay, so the layered approach is the way to go. It sounds like the classic network troubleshooting methodology, right? applied to this AI context.
Exactly. It's about breaking down a complex problem, the entire communication path from one GPU's memory out the NIC across a switch to the other NIC into the other GPU's memory into manageable, verifiable steps. It saves you from that frustrating cycle of trying random fixes and ensures you're actually homing in on the root cause. Invaluable when distributed training jobs might be costing thousands of dollars per hour in compute time.
Can you elaborate a bit on what checks you do at each of those layers, physical, network, application?
Absolutely. The layered approach is key because a problem at a lower layer, like physical, will always cause problems at the higher layers. So you start at the bottom. 1. Physical layer. Check the actual physical connections first. Are all the network cables, whether it's Ethernet or Infiniband, securely plugged in at both ends, NIC and switch? Are the cables themselves damaged, kinked, cut? Are the transceivers, like SFP Plus or QSFP modules, properly seated? Are the link lights on the NICs and switch ports actually on and showing the expected speed status? Sometimes just reseating a cable or transceiver fixes it. Basic commands like iplink show on Linux or ipstat for Infiniband can give you physical link status.
Okay, check the wires and lights first. Simple but crucial.
Yep. If the physical layer looks okay, move up to the network layer. This is about logical connectivity. Are the IP addresses, subnet masks, and default gateways configured correctly on all the nodes involved? Can the nodes ping each other successfully? Can they resolve host names via DNS if needed? Are there any firewalls, like IPtables or network firewalls, that might be blocking the specific ports needed for internode communication, like SSH, or the ports NCCL uses? Commands like ping, traceroute, epadarc, ss, or netstat are your tools here.
Checking IPs, routes, firewalls.
Got it. Right. And if both physical and network layers seem perfectly fine, nodes can ping each other, ports aren't blocked, then you move up to the application layer. This is where you look at how the AI framework or the communication library itself is behaving. For distributed training, this often means looking at NVIDIA's NCCL, pronounced nickel. Are the environment variables for NCCL set correctly? Things like NCCL debug info can give you verbose logging. Is NCCL's socket name pointing to the correct network interface if you have multiple? Are the distributed training components in your framework, like PyTorch distributed or TensorFlow multi-worker mirrored strategy, being initialized correctly? Is the code correctly performing the communication calls, like all reduce? Sometimes you might run specific NCCL performance tests, NCL tests, between the problematic nodes to isolate if the issue lies purely within the NCCL library communication, separate from your full training script.
Wow, okay. That's a very thorough, methodical process.
It has to be for these complex issues. This layered methodology connects directly to those deployment concepts we talked about and, crucially, prevents you from making costly assumptions or taking unnecessary steps like ripping out hardware before you've proven it's faulty. Find the actual problem. Don't just guess.
Excellent advice for troubleshooting any complex system, really. Hack, check, IXA, industry use cases and applications. Okay, finally, let's bring all this technical knowledge back to the real world. It's fascinating to understand the hardware, the software, the operations, but how does all this foundational knowledge actually translate into tangible impact across different industries? This last domain is about seeing how strategic infrastructure choices enable specific, often groundbreaking applications.
Yeah, connecting the tech back to the value it creates. Important context.
Healthcare AI infrastructure.
So, question 20, focusing on a critical industry. Healthcare. For medical imaging AI applications, think analyzing CT scans or MRIs, which often require real-time inference with very strict latency requirements. Maybe for immediate diagnostic support right there in the hospital. Which infrastructure configuration is generally most appropriate? Is it A, a pure cloud-only deployment, B, edge computing using local GPU infrastructure within or near the hospital, C, just using CPU-only processing, or D, batch processing only? Okay, medical imaging, real-time inference, strict latency needs. In a critical setting like healthcare, the most appropriate configuration here is definitely B, edge computing with local GPU infrastructure. Edge computing with local GPUs. Why edge over cloud in this case?
Because of those strict real-time and latency requirements, let's consider cloud only. While the cloud offers great scalability and centralized management, there's inherent network latency. Sending a potentially large medical image dataset, could be gigabytes, up to a distant cloud data center, waiting for the AI model to run the inference and then getting the result back. That round trip can easily take hundreds of milliseconds, maybe even seconds, depending on network conditions.
And in an emergency room or during surgery, seconds matter a lot.
Exactly. That kind of delay is often completely unacceptable for real-time clinical decision support, surgical guidance, or immediate patient diagnosis. CPU-only processing for complex medical imaging AI models is typically just too slow to meet real-time demands. And batch processing D, while useful for offline analysis or research, obviously fails the real-time requirement entirely.
So edge computing, putting the GPU compute power locally, right
Yeah.
there near the imaging device of the clinician, solves that latency problem.
Precisely.
It minimizes latency by processing the data extremely close to where it's generated and where the results are needed, often within the hospital's own network, maybe even on a device right next to the MRI machine or in the operating room. This is absolutely crucial for applications where every millisecond counts and decisions need to be made instantaneously without waiting for that network round trip to the cloud.
That's a perfect illustration of how infrastructure choices are directly driven by these high-stakes, real-world demands. It's not just about what's technically feasible, but what's practically necessary to deliver critical insights at the speed needed, especially in medicine. Edge AI really seems to be transforming computing in these kinds of sensitive environments.
It truly is.
But what are the challenges? Deploying and maintaining powerful GPU infrastructure at the edge, maybe in a hospital wiring closet or on a mobile cart. That can't be as simple as managing servers in a controlled data center, right? What are the unique hurdles there? You're absolutely right. It's far from simple. Deploying and maintaining GPU infrastructure at the edge, especially in places like hospitals or remote clinics, presents a unique set of challenges compared to a nice, clean, controlled data center.
Like what?
First, physical security and environmental control are much tougher. Hospitals aren't typically built with data center specs, space might be tight, dedicated cooling might be lacking, power might be less stable, and you need to physically secure the hardware from unauthorized access in a busy environment.
Right. Very different physical environment.
Second, remote management and troubleshooting become absolutely critical. You probably won't have a specialized AI infrastructure expert on site at every clinic or hospital wing 24/7. So you need robust remote monitoring, maybe using DCGM to feed data back centrally, and automated deployment and recovery mechanisms. Think about pushing model updates or diagnosing issues remotely.
Need strong remote ops capabilities.
Definitely. Third, network connectivity. While you're avoiding the latency to the cloud for inference, you still need reliable connectivity back to a central location for things like downloading updated AI models, uploading telemetry data, maybe sending anonymized data back for retraining. That edge network connection might be less reliable or lower bandwidth than data center networks.
Model updates and data syncs still need connectivity.
Yep. And fourth, maybe most importantly in healthcare, regulatory compliance gets amplified. You're dealing with extremely sensitive patient data, PHI. Ensuring that the data processed and potentially stored temporarily at the edge remains secure, private, and adheres strictly to regulations like APA adds significant layers of security and architectural complexity.
So edge offers low latency, but comes with physical, operational, and compliance challenges.
Exactly. But despite those challenges, for applications where that near instantaneous response is paramount real-time diagnostics, surgical robot guidance, critical patient monitoring edge computing with local GPUs is often the only viable architecture. It directly builds on all those hardware and operational concepts we've discussed, showing how you tailor the infrastructure to meet very specific, often life-critical industry demands. It's about putting the compute where it delivers the most value, even if it's harder to manage there.
Fascinating. A great example of applying all this foundational knowledge.
Mm.
Hashtag outro. Wow. Okay, so what does this all mean? We just powered through 20 pretty challenging questions there. We took a really deep dive, didn't we?
Yeah.
Covering everything from the foundational hardware, the GPUs, the interconnects, up through the software stacks, the containers, the optimization libraries.
Hit data management, storage strategies, deployment patterns like blue-green.
All right. Performance monitoring with tools like DCGM, security essentials like RBAC and encryption, systematic troubleshooting techniques, and finally, seeing how it all comes together in real-world applications like healthcare AI at the edge, all crucial parts of the NVIDIA Certified Associate AI Infrastructure and Operations exam.
That was quite the comprehensive tour. A serious deep dive. You listeners should feel pretty good about how much ground we just covered.
I hope so. And you should feel proud of the knowledge we explored and hopefully helped solidify.
Indeed. What's really striking, I think, is just how profoundly interconnected all these different domains truly are. You saw how storage impacts data loading, which impacts GPU utilization,
Right.
how hardware choices influence deployment strategies, how security needs to be baked in everywhere.
Yeah, it's not just isolated topics, it's a whole system.
Exactly. And mastering these areas, it doesn't just prepare you to pick boxes on an exam, it genuinely equips you to understand, to design, and to operate these complex AI infrastructures out there in the real world.
Whether you're trying to squeeze more performance out of a hyperscale cluster,
Or securing sensitive medical data for a hospital's edge AI.
or maybe designing the low latency systems needed for autonomous vehicles.
Right. You've really gained, hopefully, a comprehensive view of what it takes to be a well-informed, highly capable AI infrastructure specialist today. You're ready to think about challenges that span from, a single GPU workstation all the way up to a global network of data centers.
Absolutely. And if you are feeling inspired by all this, if you want to truly master these concepts, deepen that understanding, and go ace your NCA-AIIO certification, well, remember that continuous practice and focused study are really your best friends here.
Couldn't agree more. Knowing the concepts is one thing, being able to apply them quickly and accurately under exam pressure is another. Practice is key.
Exactly. You should explore the various interactive study tools out there. Look for good practice simulations. Find comprehensive resources that are specifically designed to reinforce these critical concepts we've discussed today. The learning journey definitely doesn't end with this deep dive. Really, it's just getting started.
Precisely. And, leveraging smart learning platforms can be incredibly effective here. Things that offer maybe AI-guided learning paths that adapt to your specific weak spots.
Oh, interesting, like personalized study plans.
Yeah, telling you what to focus on and when. Platforms that offer domain-specific practice so you can drill down on areas like networking or storage, but also mixed practice across all domains to simulate the real exam feel.
That sounds useful for building confidence and readiness.
Definitely. And full exam simulations are crucial too. Ones that really mirror the actual test environment, the timing, the question types. That helps you manage your pacing and seriously reduces that test day anxiety.
Yeah, familiarity breeds confidence.
And look for tools that go beyond just giving you the right answer. Good platforms provide targeted explanations for why you got something wrong, helping you learn from common mistakes, maybe even mistakes identified from thousands of other learners. That insight can be invaluable.
Learning from the collective experience, essentially.
Right. Things like interactive flashcards for tricky terms, maybe smart review features that focus on your errors, multilingual support if needed, even built-in productivity tools like Pomodoro timers to keep you focused. A one-stop study hub can make a huge difference.
So are there platforms like that specifically for the NCA-AIIO?
There are. One that really stands out incorporating a lot of these AI-guided and interactive features is Flash Genius. It's designed to be a smarter way to prepare, really save you time compared to just reading docs or random web tutorials.
Flash Genius, okay.
Yeah.
What makes it stand out?
Well, it has those AI-guided learning paths we talked about, adapting to your goals. It offers both domain practice and mixed practice. Crucially, their real exam simulations are designed to closely mimic the actual NCA-AIIO test environment.
Helping with pacing and anxiety.
Exactly. Plus, they have interactive flashcards, an AI-powered smart review that analyzes your mistakes and gives you those targeted explanations. It even helps you learn from common mistakes seen across many users.
That's pretty smart.
Yeah, and they offer multilingual support in 9 languages, a built-in Pomodoro timer, and a one-stop study resource hub with guides and cheat sheets. It really combines AI guidance, gamified learning elements, and smart productivity tools all in one place.
So it sounds like a modern, efficient alternative to just passively reading or using static question banks.
I think so. It's built to prepare you not just for the exam, but hopefully for success in your actual career by reinforcing understanding. If you're ready to accelerate your NCA-AIIO prep, you can start a Flash Genius free trial today and check out the certifications they cover. It's worth exploring if you want that AI-powered edge.
Good recommendation. Okay, it has been a phenomenal deep dive today into the world of NCA-AIIO. We really hope you've learned a ton, maybe gained some new perspectives, and feel significantly more confident about the path ahead, whether you're taking the exam or just working with this tech.
I hope it was valuable.
So for you, our listener, let's end with a final provocative thought to chew on. With all this knowledge now rattling around in your brain, all these concepts about hardware, software, operation security, what new complex AI infrastructure challenge are you going to be ready to design, deploy, and master